I supposed to be in class or?
I don't get, yes, you're in class. I'm just telling you, they came looking for you here. And I don't know, what's going on.
Oh, because I thought I was in the gym today, so.
You are, but they don't know that.
Okay.
Yeah, you're good.
Okay.
All right, we're doing notes. Here we go. We are starting off with what I believe is review. We are just going to be talking about linear equations and, maybe how more than one line interact on the Cartesian plane. So yesterday we did discovery activities. This is it was kind of a hopefully a nice segue into what we are working with today. So what we are working with today are systems of linear equations. So what is a system? A system of equations is a collection of two or more equations involving the same set of variables, and they're taken together at the same time. A solution to the system of equations in n variables is an n-tuple that satisfies each equation in the system. So a system is a set of two or more equations taken at the same time, simultaneously graphed on the same Cartesian plane, if we're in two space. And the solution to a system, if in two space, is an ordered pair that satisfies both or all of the equations in the system. So if I were to give you a system and I were to ask you to determine whether or not the given ordered pair is a solution to the system, and again, we have a system of two equations in two unknowns in x and y, and you are being asked to determine whether the ordered pair that I have given you is a solution. So how do you think we're going to do that? How are we going to determine if that x and y value is a solution? Absolutely. You're just going to take each equation, so equation 1 and equation 2, and I like to label my equations, and I'm going to write each equation, and as Mia said, I am just going to substitute in that x value, 0, y value, 0, for each equation, and see if I get true statements. If it satisfies both or all equations in the system, it is a solution. It must satisfy all of them. It's not okay for it to be true for one equation and not any of the others. So in this case, I get 0 equals, that's a false statement. So as soon as I realize I get a false statement, there's no way for it to satisfy both. In this case, it doesn't satisfy either. So what we would say is we would say that 0, 0 is not a solution to the system. Okay, and I would do those for each of them, each ordered pair. I'd substitute into each of them. So go ahead and do that. Substitute into each equation. So I have equation 1 and equation 2. So I'd have 2 plus 2. Oh, it works in this one. We're getting excited, but we're not completely satisfied because it has to satisfy both. Oh, what happened? It doesn't satisfy this one. So therefore, 2, 4, the point 2, 4 is not a solution to the system. And again, it has to satisfy any and all equations in the system. Now let's go ahead and do the next one. Okay, if I start substituting into the equation 1, 2 plus a negative 4 equals 4. As soon as you get a contradiction, you know it cannot be a solution. So 2, 4, let's look at a different notation, is not an element of the set of solutions, where S is the set of solutions. So it is not an element. That little E symbol is an element of. So the, yeah, if you write 2 negative, the point 2 negative 4 is not an element of the solution set. What about number 4? Is it a solution? No, we get a false statement. So 2 negative 2 is not an element of the solution set. What about the next one, 5, 1? No, not a solution. And again, as soon as you get one contradiction, you're kind of done, because remember, it has to satisfy both. What about the next one? Yes, it satisfies both of them. So I could say that the 0.51 is an element of the solution set. Or I could even say the solution set is the set of points, and in this case, it's just 1 point. There's lots of proper notations for this. Now, this is in the instance that I've given you a point and said, just verify. Verify that it is a solution. What if I give you a system and I say, graph it? Graph each of these lines on the Cartesian plane, and if they intersect, that point of intersection is the solution. So how am I going to go about graphing each of these? Well, if I look at the first one, how am I going to graph that? I'm going to put it in slope-intercept form, so that's going to give me y equals negative x plus 4. And if I want to graph that, how would I start graphing that equation? Plot the y-intercept. What is the y-intercept? 0, 4, and Miles, thank you for giving it to me as a point. If you hadn't, it would be incorrect. It would be incomplete. So there's my y-intercept, and from there, I'm going to rise and run the slope, which is, so I'm going to go down one and to the right one, and I'm going to be ever so careful. We'll see how I can graph on the iPad. I'm trying. And I could look for the x-intercept, right? When y is equal to 0, and I should get 4, right? 1, 2, 3, oh, so it should be there, right? I can always verify so that it's an accurate graph, right? By finding the x-intercept. All right, that's equation 1. Now let's graph equation 2. If I graph equation 2, I again need to put it in slope-intercept form. Okay, and what is my y-intercept? Beautiful. And from there, I'm going to rise and run the slope, which is 1. And can you tell me what the x-intercept is? 6, 0. 1, 2, 3, 4, 5, 6. So at this point, we can say that there is a solution. These two lines are going to intersect. Now, graphing will tell you if there is a solution. Really, we could look at these two equations and see that they're going to intersect. When is the only time they're not going to intersect? If they're parallel, if they have the same slope. So I can look at the same slope, they're not parallel, they will intersect, so I know a solution exists. Now, depending on how accurately you graph or what the values of each of those coordinate values are in the point of intersection, sometimes you can see it, sometimes you can't. I can look at this, and if I graphed it accurately, I can see that the solution is what point? 5, -1. So graphing will tell you if there is a solution. It may not always be easy to identify the point of intersection. So what does a solution to the system represent geometrically? It is the point or points of intersection of the graphs of the equations in the system. So if I think about that, if I think about a system of two linear equations in two variables, two lines, let's think about the different ways that those two lines can be related in the plane. How the graph of those two lines can be related. Because how those two lines are related are going to tell us how to classify the system. So there's special names that you should know of how to classify systems based on how those two lines are related. How are they related in the plane? Well, they can be related in the sense that there is one solution. So if they intersect at one point, there is one solution. The solution is just going to be the point of intersection. We would call this system consistent independent. Consistency refers to intersection. They cross. So if they cross, if a solution exists, it's consistent. If the two lines are independent, then we call it consistent independent. So you are going to be asked to classify the system using this language. You're going to have to state the number of solutions. And in the instance that there is one solution, you're going to have to state the point of intersection. The second way that these two lines could be related is, well, they could be the same line. So what points do they share? All of the points. Yeah, all of the points. So if the lines overlap, if they're the same line, we have infinitely many solutions, and we would classify this as, again, consistent because a solution exists, but dependent. They're the same line. And the third way that these two lines could be related in the plane is that their graphs could be of parallel lines. Now, we know parallel lines never intersect, so there is no solution. And we would classify this system as inconsistent. So again, graphing will tell you, or by putting both lines in slope-intercept form, we could look at the slopes and the y-intercepts, and we can see how they're related, and then we could state the number of solutions, the nature of the solutions, and classify the system. Any questions on this so far? Yes. If I ask, classify the system, you would say consistent, independent, consistent, dependent, or inconsistent. If I say state the number of solutions, one solution, infinitely many solutions, or no solution. If a solution exists and it's one solution, you have to state the point. If there are infinitely many solutions, we're going to talk about how to state the solution set. And if there's no solution, well, there's no solution to state. All right, let's talk about how we can solve it algebraically. We know we can graph these and see if they intersect the two lines, the graph of the two lines, but let's talk about how to solve them algebraically. The first method is called substitution. Now, the way you would want to maybe use substitution is you would first isolate one of the variables. Isolate a variable, one of them, choose it. I don't care which one. Sometimes it's begging you to solve it, you know, for that variable. Sometimes it isn't. I personally would look at the second equation and I would say, ooh, I could easily move the y over to the right-hand side of the equation and the 6 to the other side of the equation and isolate the y. So I have solved for y. I have solved for y in the second equation. Once I know what y is this expression, it's equal to x minus 6. So at that point, I would come into equation 1, and I would substitute that expression in for y. So everywhere I see a y, I'm going to substitute in its equivalent expression, x minus 6. Does everybody see how I just took out the y and I substituted in what I found y to be? Now, I just combine like terms on the left-hand side of the equation. If I did that, x plus x minus 6 equal 4 is going to be 2x minus 6 equals 4. Now what? How? Add 6 to both sides, and then what? Then divide by 2, and what do I get x to be? 5. Am I done? No, I need to have the point. I need to have the x and the y value. So guess what? I'm going to substitute in this value of x everywhere I see an x back in this other equation. So I'm going to substitute in 5 for x. And what do I get for y? -1. So I have x, I have y, I have my solution. The solution is the point x, which is 5, y is -1. Now, there's no reason to get these wrong, because you can always tell whether your answer is correct or incorrect. How? Substitute them back into all of the equations. If I get an identity, it's a solution. If I don't get an identity for each of these, I've done something wrong, try again. So substitution, you isolate a variable and then substitute in that expression, solve for one of the variables, substitute that value into the other expression. Another method of solving a system is by addition. Another name is elimination. Another name is linear combination. Those are used interchangeably. This is the addition method, the elimination method, or the linear combination method. So how are we going to do that? Well, first of all, you want to make sure that each of your equations are aligned. If I'm looking at these, I see my x's, I see my y's equaling a number. The first thing you do is check to see that they're aligned. If they're not, rearrange it. But they are, so I'm just going to rewrite the system down below. They're aligned. Now, I'm asking myself, how would I go about eliminating one of the variables? Well, sometimes it's easy. Sometimes it takes a little bit of work. I personally see that my x and my y, my y in my first equation and my second equation have opposite coefficients. I see a positive y and a negative y. Sometimes you don't have that. You may have to multiply one of the equations by a number, or maybe multiply each equation by a number. But ultimately, we want to add the two equations together and eliminate one of the variables. So I personally like to say which variable I am eliminating. So I'm saying I am eliminating y. The reason you're going to want to do this is because if you do say you're doing something and you make a careless mistake on a quiz or a test, I can at least see what you're trying to do and see where the mistake is. If you do not tell me what you're doing, I have no idea what you're doing if you've missed it, and it's all wrong. Okay, so I'm saying I am eliminating y by adding these two together. So let's add them together. If I add the x terms together, what do I get? And guess what happens? My y's go away. They're eliminated. Equals what? 10. Then divide by 2, and I get x equal 5. And at this point, once I have this x value, I can substitute it back into either of the equations. It should work for both. So it doesn't matter which one you choose. It is up to you. So let's say we chose number 2. And I solve for y. So my solution, again, is the set of points, and in this case, it's just, 1 point. So look how we got the same answer. This was the same system, right? The same answer for either method. And again, you can check it. So if I'm solving these and I don't have a single point that satisfies both, then I do not have a unique solution. Here you're being asked to solve the following systems of 2 equations in 2 variables and classify the system. You can graph to help determine if the system has a solution. So let's go ahead and do those. Equation in the first problem on the same Cartesian plane. How are we going to do that? What are you going to do first? Slope-intercept form. Okay, so we're going to take equation 1, and I'm going to take equation 1 and put it in slope-intercept form. That's ugly. Let me try that again. Okay, So I'm plotting it. And then I know my x-intercept is when y is equal to 0. I have my first graph. Graph of my first line. Does anybody want to do anything to that section? Is there something we can do to it to make it a little bit more pleasant to look at? Multiply by 2? Okay. So if I multiply the second equation by 2, right, that's what you're saying, then my new second equation is going to be what? Are we multiplying by positive or negative 2? Okay, multiply every one of those elements by 2, and what do we get? Oh, look at that. Look at that. So be clever, right? I could have also divided every term by point, gotten the same thing. Okay, I see. But what do we notice? They're the same line. So if these are the same line, how would you classify this system? Consistent, dependent, and how many solutions does it have? Okay, the next one. I think the next one is that the same problem we just did? It is. Okay, so we've already done this one. We're not going to do that one again. Let's look at the next one. Is anybody dying to do something first? You want to multiply the first one by 2? Okay. Or divide the second one by 2. Uh-oh. So there's my new first equation. My second equation I'm just going to bring over. Uh-oh. Interesting. Look at that system. What can you tell me about this system? They're parallel. So if I were to write each of these in slope-intercept form, I'm going to realize that I have the same slope, but different y-intercepts. So let's go ahead and rewrite them in slope-intercept form, in which case I would not have multiplied the first equation by 2. I would have divided the second equation by 2. So there's my original equation. I'm dividing the second equation by 2. I'm putting them both in slope-intercept form. And I see that my first equation has a y-intercept of 0, 4, down 1 over 1. So there's my first equation, hideous. My second equation, the graph, has a y-intercept of 0, 2, same slope. So therefore, I have parallel lines. I have no solution. And how would I classify this system? Inconsistent. Exactly. So far, so good? Okay. Now, what if we want to identify systems that do not have exactly one ordered pair solution? So if I ask you to write an example of a system of 2 equations and 2 variables that do not have exactly one ordered pair, that means they do not have a unique solution. They do not have a unique solution. Can you come up with one? If we don't have a unique solution, we have 2 cases, right? What are the 2 cases? If it's not a unique point, we said that they could either have parallel, which means they would have no solution, or they could be the same line and they have infinitely many solutions. Okay, so would you be able to come up with examples, right? So you would have to be able to come up with an example of two equations, a system, that have the same slope, different y-intercept for parallel. For the same line, one would be a multiple of the other, right? So you should be able to come up with examples to demonstrate that. Here are some practice problems. The keys are on Canvas. So these are practice. You know, I like to give you problems to help you prepare for tests. So you should be doing these problems. We're not going to do it now. You should be able to solve systems depending on whether or not I have given you the method. Like if I tell you to solve it using substitution or I tell you to use elimination, you should be able to do it. Now, let's talk about a word problem. A library is having a book sale to raise money. Hardcover books cost $4 each. Paperback books cost $2 each. Nina spends $26 and buys 8 books. We want to answer the question, how many hardcover, how many paperback books did she purchase? So we need to write a system of equations. So let's define our variables first. I'm going to say let H equal the number of hardcover books bought. And be specific. Don't just write hardcover. Let's be a little bit more explicit. I'm going to let P equal the number of paperback books bought. And you can use X and Y. You can use any variables. You're defining them. I don't care. A lot of people like to use X and Y. I don't care. Now, Nina spends $26 for 8 books. So the number of hard copy books plus the number of paperback books equals how many? 8, right? The number of books, number of H, number of P equals 8. She bought 8 books. She spends $26. Now I know that the hard copy books cost how much? So I like to write that next to my variable. You don't have to. And the cost of paperback? $2. So can we come up with another equation that represents the money? $4 for every hard copy plus $2 for every paperback is going to equal 26. There's my system. Can you solve that system? Solve it. What method are you using? Addition? Okay, you're going to have to tell me what method you're using on the test. So, what did you do first to solve it with addition? Multiply the bottom one by -2? What variable are you trying? Oh, okay. So you multiplied this one by 2. By -2. Is that what you said? Okay, so my new first equation is what? -2h minus 2p equals -16. My second equation I didn't touch. Then I added them together. And what do I get? Okay, and then I solve for h, and h is 5. And then what did you do with that? Okay, so then we went back to, you said the first original equation, and you substituted in 5 for h. That's hideous. H equals 5. So 5 plus p equals 8. So therefore p equals what? 3. Right? So the question was, how many hardcover and paperback books did she purchase? I would say Nina, because this is a word problem, purchased 3 paperback and 5 hardcover books. That's my solution. Okay, let's see if we can come up with a system to represent the second problem. Okay, an adult ticket to a school play. An adult ticket costs $5. A student ticket costs $3. A total of 460 was collected from the sale of 120 tickets. Question is, how many adult tickets were purchased and student tickets were purchased? We need to define our variables. So let A equal the number of adult tickets purchased, and let S equal the number of student tickets purchased. Again, be explicit. Don't just say S equals student. That's nonsense. Now I know that the student tickets cost $3, so I'm just making a little note. And I know that the adult tickets cost $5. I know a total of 460 was collected from the sale of 120 tickets. Name that system. Tell me what the system is. A plus S is 120. I agree. The number of student and adult tickets give me a total of 120 tickets. Now, what about money? Beautiful. Solve that system. And you can always reduce it to an easier problem to solve from the get-go if you would like. What method are you using? Addition? Did anybody make the problem easier to start with? How? I didn't hear you. Say that again. Okay, so you multiplied this one by -3. Okay, so my new system is going to be -3a minus 3s equals -360. Second equation didn't change. And then what'd you do? Okay. And what is that going to give me? Equals what? Okay. And then? Okay. Substitute. You substituted where? Okay, so we went back to the equation 1 and substituted in for A, 50. Oh, that's supposed to be a 50. And what we get for S? Okay, so how am I going to write the correct complete solution? Okay. 50 adult tickets? No. Yes. And 70 student tickets were sold. Any questions? Now this is algebra 1, right? We've seen this before. You've solved systems, you've found points of intersection. Maybe the classification could be new for some of you, but this is not new. Now, what happens? Oh, these two are, I'm going to let you, do we want to do these now or do we want to do them for practice? Practice? Okay, practice. These are practice. Solutions will be on the Canvas. Now, let's move on. If we have time at the end of class, we can go back and do them together. Let's move on and let's look at systems, but we're going to be looking at systems of inequalities. So inequalities, we're going to have to look at boundary lines. We're going to have to look at shading of half planes. And the solution to the system of inequalities is going to be the intersection of the shadings. Where is it shaded for both or all of the equations? Okay, so let's just recall how we're going to graph an inequality. This is not new. So if I want to graph an inequality, I'm going to first put it in slope-intercept, and I'm going to identify the y-intercept. Y-intercept is what for this first example? Okay, 0, -1, beautiful. Label our axes always so we don't lose points. And what is my slope? One. So I'm going to go up 1 and over 1. Oh, yeah, I have my x-intercept too. Oh, no, but what do I have to pay attention to? The boundary line. So looking at that inequality, I have a less than. So is it solid or is it dotted? It is a dotted boundary line. Okay, so I'm going to have to use a dotted boundary line. You know I take off for that. And I have to shade. Now, am I going to shade up and to the left or down and to the right? Down and to the right. But what if you didn't know that? What could you do to figure out where you're going to shade? Yeah, pick a test point. And what point do we like to choose unless it's on the boundary 0, 0. So if I substitute in 0 is less than -1, is that true? No, so this is a false statement. So don't you even think about shading the region that has 0, 0. Instead, we are going to shade the other half plane. Okay, so let's try one more example. If I want to graph the next one, I want to put it in slope-intercept form first, so that y is less than -x plus 2. When do I have to change the direction of the inequality? If and only if I'm dividing by a negative or multiplying by a negative across the inequality. What is the y-intercept here? 0, 2. And the slope? -1. And the x-intercept is what? 2, 0. Good. We like to see those intercepts. And let's check the boundary. What can you tell me about the boundary line? It is dotted. Label your axes. And which region am I going to shade? Down and to the left or up and to the right? Down, test 0, 0 if you have to. 0, 0 is true. 0 is less than 2, right? Now let's put a couple of these together. Let's solve a system. Okay? So if I'm solving the system, I do want to maybe put each of them in slope-intercept form first. So equation 1 in slope-intercept form. What is equation 1 in slope-intercept form? Y is greater than x minus 1. So we're just solving for y in the first equation. Second equation, slope-intercept form. What is the second equation in slope-intercept form? Really? You think? What was that slope? Really? What is the slope of negative 2/3? Be careful. That would change the everything. Okay, so let's graph them. We know how to do this. For the first one, am I shading above, and to the left, or down and to the right? For the first one, equation 1. Above. Now, you can either shade it, or it is okay and to just put arrows to show that you would shade above. Sometimes when you start graphing a lot, it gets a little out of control. So if you want to just put little arrows to show instead of shading the half plane, you may. For the second one, let's go ahead and plot the y-intercept. Down 2, to the right 3. Solid. And am I shading down and to the left or up and to the right? Hmm? Is that so? And again, I could have done this, right? So where is my solution set? The point where, yes. Yes. So what is that going to look like? Yes. And we have to pay attention. It's solid on this part, but dotted on this part, right? This is your little set of all possible solutions. Well, that is your solution set. Okay, I want to show you how to do these on your calculator as well as on Desmos, and then we're going to continue to work these problems. But I do want to give you an opportunity to see how you would do it on the calculator as well as on Desmos. So let's start with the calculator first. And what I'm going to do is I'm going to look at this example here. Okay? But I'm going to first look at it in terms, well, let's see how we're going to do that. Let's just do the inequality first. Let's do the inequality first. Okay, so I'm going to take out my calculator. God willing. Oh, there we go, slowly but surely. And I'm going to have to change my share screening to here. Okay. Bring that back. Ooh. Okay. So the first equation I am going to do, can you see it? How come I don't see it here? Do y'all see this? You can see this. Well, why don't I see? Well, this is very weird. Okay. Oh, I have an idea. Hang on. Sorry, I'm a little, oh, I can't, oh well. I'm doing my best. All right, so I'm going to put in the first. Oh, I'm going to put in the first one. Now, the key is it has to be in slope-intercept form for you to be able to put it in the calculator. Okay, so I'm going to say y, and and it's not equal. So I have to scroll all the way to the left and hit enter. I don't care. Some of you have color, some of you don't. Mine have color, so I'm going to choose blue. Doesn't matter. But notice here, I can change, oh, greater than, but this is less than. Which is it? It's greater than. So hit OK. So do you see how I now am showing that instead of an equality, I really want a greater than. That's greater than. So then I have x minus, oops, sorry, x minus 1. Now the next one is what? Oh, my little greater than went away. Let me fix my little greater than. Okay, now go to the next one. The next one is greater than or equal to. Now I'll tell you right now, there's no differentiating between greater than and greater than or equal to on the calculator or Desmos for that matter. So you'll just have to be aware of what your boundary line looks like if you're graphing it by hand. In this case though, it was, and I'm going to put parentheses, oh, sorry, I keep trying to type and I'm on the calculator, parentheses, and then make sure you use the negative 2 divided by 3, close parentheses, because I want to make sure that my x is in the numerator. If I don't put parentheses around the it just may use the order of operations and throw that x to the denominator, totally changes the problem. So there are my two equations, or rather inequalities, right? There's my system of inequalities. Now I want to graph it. I have no plots on, I'm good to go. Woo, look at that. Do you see your solution set? Yes. Now, for kicks, let's go back to y equals, and let's change this to equalities. And the reason I want to show you this is because the calculator can also check to find that point of intersection when you solve your system. So I'm changing these to equalities for the mere activity of demonstrating that the calculator can actually find the point of intersection, which you will not use the calculator to do, but you can check your homework. So I see where they intersect. Now, can you tell me what you think it is by looking at it? 3, 2. This is what you say. So let's now actually have it calculated. Calculate it. Go to second, trace. What do you think I'm calculating? Yeah. Now, it's telling you which is the first curve. So just choose one. It's defaulting to this blue one. So hit and enter, say, yeah, that's it. Then it jumps to the other curve, and you're like, oh, yeah, that's the second one. Now it's saying, you want me to guess it? No, I want you to find it. There it is. You were correct. So we're going to go to second, trace, scroll down to 5 to find the point of intersection. It's going to ask for the first curve, so you want to make sure that you're on the first curve somewhere. It doesn't matter. You're just identifying it. Identifying the second curve. No, I don't want to guess. I want the actual point. There it is. Hit enter again. And it finds the point of intersection. So how would you classify this system? Well, there's 2 words I need to use. Consistent, independent. Yes. Now let's go to Desmos on your computer. So the calculator can find the point of intersection. The calculator can graph inequalities, but they must be in slope-intercept form. Guess what? Desmos doesn't care. what form you give it to. So I'm going to put the original inequality that we were just working with. I have x minus y was less than 1. There it is. Now, Desmos is showing me that boundary line is dotted. Now I'm going to graph the second inequality. I have 2x plus 3y was greater than or equal to 12. Solid boundary line, there it is. And there's my point of intersection. Isn't that lovely? So here's your solution set. Right? So you can check your answers for the time being. Now, what I want you to do now is by hand solve the next 2 examples in the notes. Feel free to check your answers on your calculator and Desmos. Make sure you're proficient using each of those. So we are solving the next 2 systems, and let's see what we get. You're doing those by hand. Because on the quiz or a test, you're going to have to do it by hand. Over the weekend, while you're doing your work and your practice problems, you're checking them on the calculator and Desmos. Yes, ma'am. Yeah, but I mean, it needs to look like a line, right? Because it's a bound. Yeah, absolutely. That's up to you. I like colors. I don't know why you wouldn't graph one in one color, graph the other in another color, and show me the intersection in a different color. Wouldn't that be lovely to see? I don't care, but you know, it would be. I would at least put the little arrows for each, and then maybe shade only the intersection. You know, the little arrow showing the direction that you would for each boundary line, showing the half plane or the region that you would be shading. That's up to you. I just don't. There shouldn't be any question as to I know what you're doing. But I would denote for every inequality which direction you would shade with at least little arrows. Make sense? Okay, we should be working these, and then you're going to tell me what these are in slope intercept form, and then we're going to graph them together and see if we got them right. Bless you. Okay, I went ahead and wrote all the possible inequalities in slope-intercept form that could be written in that form if you want to verify that you're doing that correctly, because you know, if you're graphing by hand, you'd want to put them in slope-intercept form so that you could graph them accurately. And then we're going to do it on Desmos to verify your graphs. If you finish these, feel free to go back to those 2 word problems in the previous pages of the notes and work on those as well. These 2. Of course you may. Is anybody still working on graphing these by hand? Speak now or forever hold your peace. Is anybody still graphing these by hand? You need to be able to graph these by hand. Okay, nobody is saying anything, so let's just, for kicks, because it's so pretty to see, let's go ahead and graph these on Desmos. So the first system was were these 2. So you see these 2 bands. What are you noticing about those 2? They're the same slope, same different y-intercept. So what kind of lines are these? The parallel. So how many solutions do I have? None. I have no solutions. And how would I classify this system? If there's no solution, it is inconsistent system. Okay, in the next example, we had 3 inequalities. So if I look at these, the first one is this dotted boundary line shading up and to the left. This one was a nice vertical bar, all x's between -2 and 4. And then this one was a horizontal line, dotted boundary line at 3 shading below. So what is our feasible region, our region of our solution set? What shape is that? Trapezoid, right? This is going to lead us into something else that's beautiful. But this is our set of solutions right in here. Just this closed region. Okay? And you could find these, and if you couldn't identify them on the graph, you could solve systems for every 2 sets of equations and find those points of intersection. Yes. Mm-hmm. Okay, because the green is going this direction, right? And the purple's going this direction. Oh, the solution set, yes. If the boundary lines are parallel, so that would be, you are absolutely correct. The boundary lines are parallel, but with the inequality would be everything in this band would be a solution set. Yes, yes. Sorry, I'm flip-flopping between inequalities and equalities. But yes, the boundary lines themselves are parallel. So if they were equalities, there would be no solution, inconsistent system. This has infinitely many solutions. It's all points in this little region for the inequality. Yes, 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 and yes. Excellent. Thank you. All right, do those last 2 word problems, and let's talk about the solution sets to those word problems. We're working the word problems. Let's bring it to closure. Last 2 word problems. Are we able to get these? These are a little bit more complicated. Okay, are we ready to go over these? Anybody still working? Okay. The Parks and Recreation Department offers a season pass for $90. Season pass holder pays $4 for the use of tennis courts per session. Without it, you pay $13. How many sessions on the tennis courts will the total cost be with a pass and without a pass? And what will the cost be? So maybe let X equal the number of tennis sessions, right? And Y equal total cost in money. So we have two equations. We have a cost with the pass, and we have the cost without the pass, right? So can somebody tell me what the equation would be for the cost with the pass? The cost Y would be what? Beautiful. And without the pass? Excellent. So you would solve that system. Okay? So what will the cost be and how much? How many sessions would the total cost be the same? How would we find when the two are the same? Set them equal to each other. Yes, set them equal to each other. Exactly. Exactly. So did we get a solution? Maybe. Can we solve this system? It's 10. The cost will be the same. For 10 sessions, right? Is that what you said? Oops. And how much would that cost be? Would be what? $130. Okay, do the next one and check your answers because we're out of time. Are there any last minute questions? No? Okay. Y'all have a wonderful weekend. Be safe. Maybe I'll see you in tutorials to like review your test. Maybe not. Bye. You're welcome.
Thank you.
You're welcome. I know you're coming to review your test.